Most of us were taught that life is a series of individual choices. You work hard, you get paid. You study, you learn. But there is a deeper layer to reality that most people never see. In the lab, we call it the invisible board. Every interaction you have, from a simple salary negotiation to a high-stakes superpower standoff, is a game. Not a game in the sense of a hobby, but a game in the sense of a mathematical structure. To see the board, you only need to identify three things: the players, the actions, and the payoffs. But here is the catch that changes everything. In a true game, your success does not depend on your own choices alone. Your outcome is inextricably tied to the choices of everyone else. You are not a solo actor. You are a piece of a connected geometry. Once you understand this, you stop looking at the world as a chaotic series of events and start seeing it as a predictable map of strategic tension. The calculus of interaction. Before we can master the game, we have to define what it actually is. Game theory is not the study of games in the way we think of chess or cards. It is the formal study of strategic decision-making. In classical economics, we often assume a rational actor exists in a vacuum, someone who looks at a price tag and decides if they want to buy. But in the real world, no one acts in a vacuum. Game theory is the bridge that connects your choices to the reactions of others. It is the calculus of human interaction. It assumes that every player is trying to maximize their own payoff, but they are doing so while knowing that every other player is doing the exact same thing. It is a mental hall of mirrors. You are thinking about what they are thinking about what you are thinking. This isn't just philosophy, it is a rigid mathematical framework. By assigning numerical values to outcomes, what we call utility, we can actually map out the gravity of a situation. We can see where the tension lies and predict exactly where a conflict will snap. Whether we are analyzing a trade war, a digital auction, or the strategic depth of a naval blockade, we are simply looking for the lines of force on the invisible board. Once you see these lines, you realize that most chaos in the world is actually a very disciplined, very predictable set of mathematical moves. And nowhere is that discipline more visible or more dangerous than in the trap we call the prisoner's dilemma. The prisoner's dilemma, the trap of self-interest. If the world is governed by logic, why do we see so much collective failure? Why do we see massive corporations destroy their own profits in price wars, or nations deplete the very natural resources they need to survive? To understand this, we have to look at the most famous broken game in history, the prisoner's dilemma. Imagine two players who would both be significantly better off if they cooperated. It is the obvious, common sense choice. But the math of the game contains a sinister trap. When you look at the board from the perspective of pure self-interest, the logic forces you to betray your partner. If you both cooperate, you both win. But if you cooperate and the other person betrays you, you lose everything. To protect yourself, you betray them first. When both players follow this perfectly rational logic, they both end up in the worst possible outcome. This is the trap of self-interest. It is the mathematical proof that a group of rational individuals can, and often will, make a collectively disastrous decision. Whether it is a high-tech hallucination in a boardroom or a tactical move in a narrow shipping lane like the Strait of Hormuz, the dilemma is the same. When we can't trust the other player, the math of survival makes truth the first casualty. The Nash Equilibrium, the point of no return. If the world is a game, then every game has a destination. In the lab, we call this the Nash Equilibrium. Named after the mathematician John Nash, it is the skeletal structure of human interaction. It is the moment where the music stops and the board freezes. Mathematically, a Nash equilibrium occurs when every player in a game is making the best possible move they can, given the moves of everyone else. Think about that carefully. It means that even if you aren't in a perfect situation, you have no incentive to change your strategy, because any individual move you make would only make your outcome worse. You are locked in. This is the truth of the standoff. It explains why the world often feels stuck in mathematical ruts. Take biological ecosystems. Why do two different species of trees in a forest grow to the exact same height, even if it exhausts their nutrients? Because if one tree stops growing to save energy, the other will overshadow it and take all the sunlight. They are trapped in a Nash equilibrium of height, a mutual exhaustion where neither can afford to stop. Take global markets. Why do two gas stations often sit directly across the street from one another, instead of spreading out to cover more of the city? If one moves away to find a new neighborhood, the other will simply take over the entire central hub. They settle at the center, not because it's the most efficient for the customers, but because it is the only stable point where neither can gain an advantage by moving. This is the point of no return. It is why political borders often remain frozen for decades, even when both sides hate the status quo. It is why price wars reach a floor that no one can drop below without going bankrupt. When you look at a skewed curve or a stagnant economy, you aren't looking at accidents. You are looking at the invisible gravity of an equilibrium. The players haven't stopped moving because they are tired. They've stopped because the math has boxed them in. Once you can identify these ruts, you realize that the only way to change the world isn't just to try harder. It is to change the rules of the game itself so that the equilibrium shifts to a new, better coordinate. But as we will see in the Strait of Hormuz, sometimes the equilibrium we settle into is a hair trigger away from total collapse. Zero-sum versus non-zero-sum. In the popular imagination, every victory requires a victim. We are taught that the world is a giant pie of a fixed size. If I take a bigger slice, your slice must, by definition, get smaller. In the lab, we call this a zero-sum game. The math is simple and brutal. My gain plus your loss equals 0. This is the geometry of the literal battlefield. If one army captures a hill, the other loses it. There is no new value created. There is only the redistribution of what already exists. It is a game of pure friction. But here is the myth that holds most of the world back: the belief that all of life is zero-sum. Game theory shows us a much more elegant possibility: the non-zero-sum game. This is a win-win geometry where the total value, our soup pot, actually grows based on our interaction. When a software developer writes code that automates a task for 1 million people, value isn't being taken from anyone. It is being generated out of thin air. The spoonful of soup theory we discussed previously depends on this. If the pot is well stirred and the ingredients are right, the act of sharing data and collaborating doesn't just divide the soup, it creates more of it. The most successful civilizations in human history are those that figured out how to move the invisible board from a zero-sum struggle for land to a non-zero-sum engine of innovation and trade. They realized that if we stop trying to steal each other's slices and start focusing on the chemistry of the dough, the pie itself expands. But we must be careful. The transition between these two worlds is fragile. When trust breaks down, as we see in trade wars or the strategic maneuvers in the Strait of Hormuz, a non-zero-sum engine can collapse back into a zero-sum fight for survival in an instant. Understanding which game you are actually playing is the difference between building a future and burning one down. The human glitch, fairness and spite. If we were all cold, calculating machines, the world would be easy to predict. But as any project manager in a dusty village or any diplomat in a war room will tell you, the rational actor model has a massive built-in human glitch. To see this glitch in action, we use the ultimatum game. Imagine I am given $100. The rules are simple. I have to offer you a portion of that money. If you accept my offer, we both keep the cash. If you reject it, the money vanishes, and we both get 0. Pure mathematical logic suggests that if I offer you $1 single, you should take it. After all, $1 is better than 0. But that isn't what happens. In study after study, across every culture on Earth, people reject low offers. They would rather lose and get 0 than see someone else get an unfair 99. This is spite. It is a biological drive to punish unfairness, even at a personal cost. It is the moment where the payoff isn't money or resources, but the emotional satisfaction of justice. In the lab, we realize that humans are pattern-seeking machines, but we are also fairness-seeking machines. We will burn the invisible board to the ground if we feel the other player is cheating. This glitch is why trade deals collapse over minor ego slights and why wars continue long after they have stopped being profitable. When we look at the geopolitical tension in a bottleneck like the Strait of Hormuz, we aren't just looking at the math of oil and insurance premiums. We are looking at the math of dignity, honor, and spite. If you ignore the human glitch, your model is a high-tech hallucination. You aren't holding a map, you're holding a fairy tale. To truly master the data, you have to account for the fact that sometimes the most rational move a human can make is to do something completely, defiantly irrational. The evolutionary stable strategy. If life is a game, how do you actually win it? The answer isn't found in a single round or a one-time victory. It is found in what we call the evolutionary stable strategy, or the ESS. In the lab, we move from the snapshot to the cinema. We look at iterated games, situations where the same players meet again and again, year after year. In this environment, the math changes. A strategy that works once, like a sudden betrayal or a ruthless zero-sum grab, might fail miserably when played 1,000 times. In an iterated world, your most valuable asset isn't your cleverness, it is your reputation. Evolution has taught us that the most successful strategies are often nice, retaliatory, and forgiving. You start by cooperating, you punish betrayal immediately to maintain deterrence, but you are willing to return to cooperation if the other player does the same. This is how chaos turns into perfect order. Over generations, societies that settle into stable, cooperative ruts outcompete those that remain in a state of constant, spiteful war. The math literally favors the builders over the looters in the long run. But a stable strategy is only stable as long as the environment holds. When a new variable enters the equation, a resource scarcity, a technological shift, or a sudden military buildup in a place like the Strait of Hormuz, the old ruts can vanish. The skeletal structure of the world begins to shift, and a strategy that was stable for 50 years can suddenly become a death trap. To survive the game, you don't just need to know the rules of today. You need to understand the calculus of change. You need to know when the board is being tilted and when the truth you've relied on is about to be rewritten by a player you never saw coming. We have seen the board. We have mapped the ruts. Now, it is time to look at the world's most dangerous game of chicken. In the next experiment, we go to the edge of the map. We go to the strait.